Today we're going to talk about compound interest, population growth and decay, and depreciation. The formulas we're going to need to memorize are A equals P times the quantity, 1 plus R over N, raised to the NT power, and A equals PE to the RT. Let's begin with A. A is our final amount. What will we end up with? P is our initial amount. What did we start with? How much money did we invest? How many people currently live in the place that we're talking about? What is the price that you paid for your automobile or your iPod? 1 is obviously 1. R is the rate. So in both of them, R is the rate. Notice that the rate appears as part of the base in this formula, and it appears as part of the exponent in that formula. T is time, which we often mark in years. So although it could be time in minutes, time in hours, time in months, but most often it's time in years. In this formula, the one unknown is N. N is the number of times we compound each year. So this formula is often used for money. And so if we compound annually, N would be 1. If we compound monthly, N would be 12 because there are 12 months in a year. And essentially, let's say we compound monthly. What we're doing is we're taking the rate that we get and dividing it into 12 equal parts, and then saying in each year, we're applying that 12 times. So you're getting interest more frequently, so the money that you're making is making money more frequently. In this one, the unknown is E, but E is not an unknown. E is actually a number. It goes with things that grow naturally or continuously. And E is approximately 2.718, and there are 2 buttons on your calculator that actually do E. One of them is the second function of divide, which actually is just E itself. Often we raise E to powers, so the other place you will find it is as the second function of natural log. So it's waiting for us to put a power on it if we use that one. Okay. In this expression, the base is 1 plus R divided by N. And if the base is bigger than 1, then our initial amount is going to grow. If the base is between 0 and 1, then our initial amount is going to decay. In this, since E is the base, and E is definitely bigger than 1, it seems like the only thing this could do is grow. But if we make the rate positive, we grow. If we make the rate negative, we actually get decay. Okay, so let's put this to work. We have $800, and we can get an interest rate of 2.5% for 12 years. And the question is, how much money will we have if we compound annually, if we compound quarterly, and if we compound continuously? So if we compound annually, the amount we will have would be our $800, our initial amount, 1 plus our rate, which we have to convert from a percent to a decimal, so 0.025. Annually means once a year, to the 1 times 12 power. To compound quarterly, we're going to have our $800, 1 plus our interest rate, 0.025, quarterly, once a quarter, means 4 times a year to the 4 times 12 power. And continuously means we need the other formula. So it would be $800 E to the 0.025 times 12. Notice now the rate is in our power rather than as part of our base. No one does these problems in their head. Everyone does them with a calculator. So the first one, 800, 1 plus, 1 plus 0.025 divided by 1. Which technically we don't have to do. Raised to the, now if I can do the power in my head, I don't need to put it in parentheses. 12 times 1 is 12. So we have about $1,075.91 if we round properly. For our compound quarterly, okay, we're dividing our rate by 4 and then raising it to the, now if I can do 4 times 12 in my head, I don't need parentheses, but let's assume I can't. Because there will be ones that you can't do in your head. Okay. So now we have slightly more money if we've compounded 4 times a year. And then continuously, which is our other formula, E to the, and I definitely need a parenthesis around this, 0.025 times 12. Okay, so that's the most money I can make if I compound my $800 continuously. So in 12 years, I could make $1,079.89. So not big jumps, but you do make more money if you can compound more frequently. Okay, let's try something else. Let's talk about population, which does tend to grow continuously. So we may have 28,000 e to the 0.06t, or maybe 28,000 e to the negative 0.035t. And just to interpret what we're seeing, what this says is that the current population is 28,000, and because the power on base E is positive, that population is growing. This one also says the starting population was 28,000, and since the power is negative, that population is getting smaller. So people are moving away from this town, or something worse. So in 5 years, we would just plug in a 5 for t in each of these formulas. Okay, so this is showing 6% growth, and this is showing 3.5% decay. Okay, so for the first one, we have 28,000 E to the, and I need parentheses for this, 0.06 times 5. Okay, so the town now has 337,796 people. And need parentheses again, negative 0.035. As you can see, the population got smaller. Now there's only 23,505 people in the town. Okay, let's take an iPad, which you know, the minute you buy it, it starts to lose value. So if we put it in a continuously losing value type model, it might look like this. I paid $400 for it, and it's losing 25% of its value each year. This one is saying, this is a sort of an annual model. So let's suppose I know that it's losing 20% of its value each year. So it's taking one, and instead of adding value, I'm subtracting value. So what this is going to create is a base that's less than 1, bigger than 0, but less than 1. So this is how an annual model might look if it's losing value. This, again, is how a continuous model looks with a negative exponent. So let's look at this in table form. So let's take this one first. So what I did was I typed in 400e to the negative 0.12x. Oops. So now I have to fix that because I typed in the wrong thing. Negative 0.25, because I didn't realize it probably loses value a lot faster than just 12% per year. And then if we go to our table, we can see that its initial value at year 0 was $400. After a year, you could resell it for $311.52. After 2 years, you could resell it for $242.61. After 3 years, you could resell it. And what I want you to notice is that in an exponential model, it never becomes worthless. So even, let's say, 25 years, owning it for 25 years, it's still worth 77 cents. And you could keep going. It'll never be worth nothing. Okay, so let's take the annual model and see how that's also showing that we're losing value. Okay, so 1 minus 0.2, which I know is 0.8, raised to the x power. And I'm going to start my table again at 0. So let's take a look at our table. Again, it's showing when you buy it, it's worth $400. After a year, you could sell it for $320, then $256, then $204.80. And again, it's never going to be worth nothing. It's still worth something. And even, so it's worth like 13 cents in 36 years. So that's an exponential model. Again, I just picked these rates off the top of my head. I don't really know how much iPads depreciate by or what their starting costs are, but I just wanted to show you that a negative power on base E will cause decay, and a number between 0 and 1 will cause decay in an annual model. I believe that's it.